Okay. So, in the last class we are considering applications. So, one category was the forward modeling, and that time what I did, I showed that if there is an unknown system with some impulse response coefficients, FIR system, FIR model for the system, I do not know, maybe I took capital up to capital N. So, okay. So, if you give a WSS 0 bin random process at the input, and the noise which gets added in various parts of the system, the entire noise effect you can add at the end, call it Zn, and this noise is 0 bin and statistically independent with Xn. Then if we have shown that if I have an optimal filter W0 dot 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 Wn minus 1, and in this I take as Dn. So, essentially this error is to be minimized, this variance is to be minimized, this is Dn. Okay. Then we showed that optimal filter, there is W is W0 dot 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 Wn minus 1. So, W opt will become W opt is W opt, actual optimal filter is nothing but the filter coefficient vector H. So, if I can compute W opt from the autocorrelation matrix of Xn and cross correlation between Dn and Xn, okay, that is or inverse P. In that case, from W opt gives us this unknown system parameters, which is fine. But as it is, I mean, we often do not know the statistical behavior or statistical properties of the input. Two inputs are here, one is Xn input, another is the desired response input. I mean, I need the statistical properties like the autocorrelation of the input and the cross correlation between the two. Okay, Dn and Xn or all samples of Xn. Now, these things may not be static in time, they change with time. That is why we cannot have a optical filter computed once for all. Okay. That is why you have to make it adaptive. For instance, suppose these filter coefficients, suppose Xn is such that the input autocorrelation matrix is fixed, it does not change, input statistics is not changing, but still this if the system coefficients are changing from time to time, maybe very slowly, but changing from time to time, then when we have one set of coefficients, then I know what is Dn. Dn is Xn transpose H, Xn is the data vector, we have done all this in the last class, input data vector at the current time. So, this is a convolution output X transpose H here plus Zn, and we know what is P vector, because W opt is R inverse P. R is fixed, input statistics is not changing, suppose, but if the system coefficients change, that will affect this output and therefore Dn, and if Dn is affected, P will change, that is what I am saying, I am showing. So, P is E of Xn Dn. So, as we have seen in the previous class, if I replace Dn by this, E of Xn with Zn will be 0, because they are statistically independent, each having 0 bin. So, it will be E of Xn into E of Zn, each is 0 bin, gone. So, you will be left with E of Xn, X transpose n, H. So, it will be R H. Now, suppose right now I have some H vector. Okay. So, for that a particular P, I calculate R inverse P, and that gives me an optimal filter. From that I find out H. But if H changes from time to time, okay, then what is now P will not be P in future. Okay. So, current R inverse P, current W opt will not be equal to your H vector in practice. In fact, these filter coefficients may be continuously time varying, but in a slow manner. So, in such cases I cannot go on computing R inverse P like this, right, at all points of time. So, I have to make it adaptive. So, therefore, if you want to make it adaptive, it will be like there will be function of n This is an adaptation part, maybe a adaptation, example LMS. So, you take this En and use the LMS rule to change these coefficients. These are schematic we have shown for adaptive filters, right. So, this forward modeling of adaptive filter, forward modeling by adaptive filtering, forward modeling of an unknown time varying system by an adaptive filter, this is a general scheme. Now, I will take up some special cases of this, special applications of this. Okay. Example 1, adaptive echo cancellation. What happens? Consider a telephone line. This is line. Actually, this is not a single line. Along with this, there is a ground line, but ground line I am not showing. This is common for all places. So, through this signal comes, speech signal from a distant speaker comes to this end, and there is something called a hybrid device. What it does is this, at this end I got a speaker, is a microphone, a speaker. So, what the hybrid does is this outgoing signal it channelizes to this side, and this incoming signal it channelizes to the speaker side. So, he is ideally the speaker, this speaker here will be hearing this incoming signal, but his own speech will not come back to him, will go in this path. Okay, there is the ideal hybrid. But problem is, these ideal hybrids do not exist in practice. Often they are found to be leaky. Leaky in the sense, part of this signal ideally should have gone entirely to the speaker side, none should have leaked out. But in practice what happens, a part of the signal maybe after passing through this filter in another form, some kind of distorted form, goes through the hybrid in this direction. So, it gets mixed with the incoming speech from this speaker, which goes of course in this direction, and this leakage component also goes in this direction. So, this leakage component also reaches the distant speaker, he hears it as an echo, and this echo is often very disturbing, especially if the distance is large, like what you have in satellite phones. If the distance is large, then obviously there is a gap between what he told and what is hearing, because what he told, it was some time ago, then it took all the time to reach here and coming back, twice the journey, twice the distance. By that time his own speech has finished, but even if this guy does not speak, even if his own speech has finished, that now part of it now comes back as an echo. So, he distinctly hears the echo, which is very disturbing. Okay. And this is not only in the case of telephone line, even one faces the same problem in data network. In data network, this will be carrying data, incoming data that will go to a server at this end, and server's data will come through this path. So, if the hybrid is leaking, part of incoming data will get mixed with the server's data. So, whatever goes in this direction will be erroneous. Okay, it will be like added with some kind of noise coming from this side. So, we have to cancel this. So, what we do? The hybrid we model as an unknown system. We have already shown that unknown system in the previous slide, previous page, unknown system, and model it by an FIR filter. All right, model it by an FIR filter. So, this actually is like this. So, the leakage generating mechanism, that part, not the entire hybrid, the leakage generation mechanism which takes this as input and gives a leakage component here, that we take as, that phenomenon, that process is my unknown process, unknown system. Okay. That leaking phenomenon, the leakage part of this hybrid. Okay. So, that is an unknown system. So, we take it to be linear and model it by an FIR filter, maybe H0 ... H n minus 1. So, if xn is the input, this xn convolved with them, these coefficients, filter coefficients, that will be the output. This is the leakage component, and that gets mixed with this fellow's speech. So, this fellow's speech is coming here like this, maybe Vn. So, what goes out is this component. Okay, let this component be Un. So, this is the leakage disturbance. Un plus Vn, it goes out to this direction. So, what I do is like an now I am able to see it in a system identification framework, where this is an unknown system. It is driven by an input, and this is the output, and this is like a noise in that context. In the previous system identification context, there was an additive component which was noise there. It will be something like this, because V of n and x of n, they are statistically independent, because this is from this speaker, this is from this speaker, there is no connection between them, and they are, you can take them to be zero mean. So, they are zero mean statistically independent. Okay. Therefore, the previous theory, the theory of the previous thing, that system identification thing will work. If I could have an optimal filter here, okay, this output, and if I take this as Dn, because remember in that unknown system identification problem, system output plus that additive component which was noise there. In this case, it is the speech signal. So, it is not a noise, but then it is statistically independent with xn and 0 mean. So, you can apply the same theory here. So, this system output plus this component, they get added. If I use this as Dn and this as xn, and this is an optimal filter, FIR filter, then we know that optimal FIR filter will be nothing but these fellows, H0 to Hn minus 1, which means Un and this will be same. So, this will also produce Un. If I could make an optimal filter, it will be Un. So, if I subtract Un from here, so this Un will go. So, what will go here is Vn. So, the echo part ideally is cancelled, but optimal filter, we cannot do, because system parameter may change, input statistics may change from time to time. So, I cannot have, because the speaker may change. So, the statistics of input can change, optimal filter can change. Okay. So, I cannot put an optimal filter here, I have to make it just adaptive. So, adaptive filter AF, adaptive filter. So, what it does, filter output Dn minus the filter output this and this Xn, these are used in adaptation. Adapt the filter output Dn minus this is the error. Error is equivalent to error. So, En is given to the adaptive filter, Xn is given, and it changes the coefficients like this. Remember, as when it is adaptive filter, since adaptive filters converge only in mean, not absolutely. So, in the previous slide also I forgot to mention, one minute. That adaptive filter coefficients, if they are, under optimal filtering, they would be ideally equal to this unknown system coefficients. But here adaptive filter means the coefficients will be, each coefficient will be fluctuating around the corresponding optimal value. Okay. But mean, that is expected value of that fluctuation, will be equal to the true system value, this parameter. So, we make sure that the fluctuation ranges are small by adjusting mu. In fact, it is known that in mu, the step size in the LMS is made very small, fluctuation range will be small, and with that we are happy. So, technically it is not an actual optimal filter. So, it will not be exactly equal to Un, there will be some error, coming because of the fact that adaptive filters do not converge absolutely, they converge only in mean. So, any time the coefficients here will not be exactly equal to H0, it will be fluctuating around, particular H, say you consider the H0, corresponding coefficient here, because it is adaptive, it will be fluctuating around H0. So, that mean of the fluctuation is H0. So, it will not be H0 always. So, since it is fluctuating and same for all the coefficients. The filter output will not be exactly equal to un, there will be some error, but the error will be less because by adjusting mu we make sure the fluctuation ranges is very small. Okay. So, this is a very simple example of adaptive echo cancellation, and in this topic lots of research have gone, more and more, many interesting structures have come up and all, tons of research have gone into it, but that is all old now, 70s, 80s, 90s, but still a very important topic. Next example. This is the example I gave in the very beginning of this course. That is, maybe in the digital domain you are given a signal x n which has a discrete time cosine, sinusoid function, like a cosinusoid a cosine some particular omega c for carrier omega c n plus phi. Phi can be a random phase, so it is a random signal, you can say. Every time you observe you get same cosine waveform, but time shifted because of this phase. Phase takes values from 0 to 2 pi randomly. So, it is a random thing. Okay. Plus noise. So, this is a sinusoid signal which is mixed with some noise of high reasonable, some high power. So, SNR is not high. Then I said that if you want to remove noise as much as possible, you should design a band pass filter where very sharp, very narrow band, center frequency omega c, and here also very narrow band pi minus pi. This is your okay. If you can design like this, then what will happen? This noise is wide band, maybe white noise. So, all the noise outside the pass band will go. So, most of the noise, almost 99% may say, will be gone because the filter is very narrow, in all other places 0. But it will capture this signal because its center frequency omega c. So, in impulse response will be, if you take a discrete time Fourier transform, that will be an impulse at omega c, another at minus omega c. So, they will pass, and therefore, you will be able to get back this signal maximally. But problem is in this approach is that if after some time the frequency changes, then this filter will remove this input also, because now omega c has changed to some frequency, say here. Some frequency may be here and here. So, my pass band should have been here now, okay. But that is not the case. That is, my pass band should have been here and here. It is now omega c prime minus omega c prime. Omega c has changed to omega c prime, but that is not the case. I have designed the filter once for all. So, filter remains as it is, centered at omega c and minus omega c. Therefore, if this frequency changes from omega c to omega c prime, after some time the frequency changes, it falls outside the pass band of this filter, okay, and therefore, signal also is gone. So, this is not the way to do. Okay. So, how to still recover this adaptively? That is what this adaptive line enhancer. Line, because if you take this as a random process, its autocorrelation function again will be cosine, because it will like a cosine this and a cosine omega c within bracket n minus k, if k is the gap, plus phi. So, a square and cos into cos will give rise to cos. Effectively, it will be a cosine function of k. You can work out, take it as an exercise. So, if you take discrete time Fourier transform of that, you will get the power spectral density. Power spectral density, if it is cosine, it will be impulses at omega c and minus omega c, that here and here. Impulses are like line. So, line spectra, power spectral density coming from here, and Zn, this is a white noise in general. So, its presence will be everywhere. So, our purpose is to enhance the line, that is removing the noise as much as possible and therefore enhancing the impulses. Okay, that is why it is called line enhancer. It is done adaptively, so that even if the input frequency changes, our previously designed filter adjusts itself, adapts itself to the new filter. a new filter with this passband, and so on and so forth. Okay, that is what I will do. Again, we will be using the concept of the forward modeling, but before that, you need to know something, some fact which maybe you do not know. So, see one thing, suppose I give you Sn as some a e to the power j omega c n plus phi. Instead of cosine, I am taking complex sinusoid, fine. Cos you can always write as e to the power j theta plus e to the power minus j theta, like that, e to the power j this plus e to the power minus j this by 2. Okay. So, Sn, what is Sn minus 1? If you put n minus 1 here, so one component e to the power minus j omega c, okay, that will go out. We put n minus 1 here. So, omega c into minus 1, that part e to the power minus j omega c goes out, and remaining remains same, e to the power minus j omega c n plus phi, which is Sn, which means Sn is e to the power plus j omega c is n minus 1. So, if I do the Z transform of both sides, okay, it will be capital Sz, and here it will be this times Z inverse capital Xz. If you take everything on one side, it will be 1 minus so this is a first order polynomial in terms of Z inverse. If such a polynomial, it is called annihilator, because it annihilates Sz. If you multiply this Sz by this, you get 0. All right. Now, suppose you got not just one, you have got many. Suppose Sn has some a1 e to the power j omega c1 n plus phi 1, which I call signal S1n. Then another component a2 or maybe dot 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 ak, take the general case. E to the power j omega c k n plus phi dot 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 dot, maybe you have got p fellows, e to the power j omega c p n plus phi. Okay, this is my skn, this fellow is skn, and like that. Okay. And if I had only this, then I know if I construct a polynomial like it is 1 minus e to the power j omega c1, so omega c1 z inverse, that into S1z 0. Similarly, here from here, if I call it skn, and if I construct a polynomial 1 minus e to the power j omega c k, this k, omega c k z inverse, that into capital Skz equal to 0, and likewise. So, suppose I form a product polynomial, that is 1 minus e to the power j omega c 1 for this first guy, z inverse, the polynomial for the first, dot 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 dot, I am multiplying them now, 1 minus e to the power j omega c k z inverse dot 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 1 minus e to the power j omega c p z inverse. If I have this product, okay, and this product let me call a, not a, let me call maybe qz. Then question is, what happens to Qz into Sz. Sz is summation of S1z plus S2z plus dot dot dot. So, this is nothing but Qz into S1z dot 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 is Kz dot 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 is Pz. Now, Qz into S1z. Okay, Qz is this much into S1z, but this is a product of the first order factors, this into the. So, I can always bring this factor in the first position, isn't it? I am multiplying the factors. C A plus B into C plus D is same as C plus D into A plus B. So, I can bring this in the first, and then if I multiply S1z by that. So, this first polynomial, this will first work on S1z, but that will be 0 because of this theory. So, if other polynomials then multiply, still they will multiply 0, anything multiplying 0 is 0. So, that will become 0. I hope you understand this. S1z and Qz, Qz has this factor, S1 has e to the power j omega C1, okay, and e to the power j omega C1 z inverse 1 minus this first factor in this chain, the product. But product of these factors I can always shuffle, I can bring the first guy in the very beginning. So, that into S1z because of this theory is 0, and remaining factors multiplying 0 is 0. So, Qz into S1z would be 0 plus dot dot dot, say you consider Skz, this guy. When I am multiplying Skz by this Qz, Qz times Skz, I will pick up this polynomial 1 minus e to the power j omega c k z inverse. I will bring it to the front, and so that will first work on, that polynomial will first work on Skz, and that is 0. So, whole product is 0. Understand? When the same Qz I am using to multiply Skz, that time I will pick up not the first polynomial, but the kth 1 minus e to the power j omega c k z inverse. So, if I bring it to the front, so first that will multiply Skz, but because of this theory that is 0. So, I will get 0. So, that way 0 plus dot 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 0, which is 0. So, this means Qz into Sz, this is my Qz, right, this is my Qz, Qz into Sz is 0, but now if I consider the product 1 into 1 into 1, so first term will be 1 and there are p terms, okay, so it will be altogether highest power will be z to the power minus p, and coefficients can be complex, I do not mind. So, it will be a polynomial like some 1 plus, just a minute, it will be a polynomial like 1 plus maybe alpha 1 z inverse, alpha 2 z inverse 2, alpha 1 alpha 2 are coefficients, if you multiply and carry out the whole product, these are the coefficients, they can be complex, but this is a polynomial up to order up to power z to the power minus p, because there are p factors. So, this is my Qz, when you multiply, this is my Qz. So, Qz into Sz equal to 0. That means, in time domain it will mean what? Sn with Sz into 1, Sz, if you keep that on one side, Sn, and bring the others on the left hand side. So, minus alpha 1 z inverse Sz. So, minus alpha 1 z inverse Sz, S is the summation of all. So, alpha 1 S n minus 1. Similarly, minus alpha 2 alpha 2 is n minus 2 dot 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 minus alpha k, or no need to have alpha k, you can directly go to the last term, alpha p S n minus p. That means, in this case, current sample can be given exactly as a linear combination of past p samples. That is why it is purely predictable. Any current sample of Sn can be obtained by a linear combination of past p samples, as though if I have a filter that takes Sn minus 1 as the input, and I have these coefficients as the filter coefficients minus alpha 1, minus alpha 2, minus alpha phi, then filter output will be same as Sn. Okay. So, this fact will be used in that adaptive line enhancer, and that I will show in the next class. Okay. Thank you very much.